I'm Bryce, and I'm going to be talking about practical functional programming. So can I get a quick show of hands who here is familiar with C++ 11 lambdas? All right, most of you probably shouldn't be in this talk. Who here is really, really, really familiar with C++ 11 lambdas? All right, it's a little bit better. OK, so I'm going to is this thing going to work? Yes. I'm going to mostly have sort of 3 sections to this talk, and I'm going to have a couple examples covering sort of 4 areas that I think functional programming is important in C++. The first one is, I think, the most obvious, which is sort of these powerful generic algorithms that you see in the standard algorithms library. So std sort is kind of one of my favorites because everybody knows what it does. And so in std sort, we've got this one overload that takes a compare operation. And so that is a function object that it's a binary operator, and it just says, how am I going to do the comparison to actually sort this sequence of things? So that makes this a higher order function, which we'll talk about a little bit later. But the really powerful thing here is that you've sort of got this library where you can plug in all these functions that sort of drive the algorithms. So it lets you write these very, very, very generic routines and then use them to build your specific algorithms for your code. The second thing is reactive programming. So that's where you've got some stuff that's going on, some events, and you want to write reactions to those events. So a user clicks a button in a GUI, and somewhere, there's in your whatever interface you're using, Qt or whatnot, you've got some callback that's going to be invoked that's going to do something in response to that. Or you've got an asynchronous threaded server that is taking in network requests, and it's got some callback that it's going to invoke to deal with those events. Or what I deal with mostly is sort of threading and I/O. So I've got different tasks. I'm waiting for them to complete. I want to sort of manage my execution flow. And all these things are sort of non-imperative in the sense that you've got events, and you're writing reactions to them. So the third thing is this sort of a capability to take an existing function and turn it into a function that you're going to call in a different fashion. So I think this is really useful, especially when you're dealing with legacy codes. You want to call something in C. You want to call it with more arguments, less arguments, change the orders of arguments. And finally, you sort of have this capability to express algorithms as a first-class object that you can store in your data structures, you can pass around, you can update, so that you can have a much more dynamic coding experience. All right. So these are sort of the 3 sections I'm going to talk about. I'm going to only really talk about 3 things, which is 1, first-class functions, 2, sort of higher-order functions, and then 3, some stuff with parallelism, which I'm going to not get into right now because it's a little bit more complicated. So according to the Purple Book, which is a very famous book out of MIT for how to write a scheme compiler, these are the 4 requirements for an entity to be considered a first-class citizen of a language. It has to be something that can be named by variable. They have to be able to be passed as arguments to procedures. You should be able to return them from procedures. And you should be able to include them in data structures. So question, who here thinks that in C++ functions are first-class objects? Who here thinks we have ways in C++ that we can represent functions as first-class objects? OK. All right, so prior to C++ 11, there were a lot of different ways to express functions as first-class objects. We use the term function object a lot. I'm not going to use that term at all in this talk for the simple reason that it's a concept now in C++11, and it's a concept which types that are considered callable implement. And I like the callable concept better because the callable concept covers things like pointers to member functions, which, of course, a pointer to a member function can't really be invoked in the same syntax as a pointer to a function. Because for the pointer to the member function, you need to have the object, you need to do the dot, then the method name syntax. But we're going to talk a little bit later about there's a generalized way to invoke anything that's a callable object. So the idea of a callable is just something that there's a way to invoke it. And it's just this black box routine. There is some routine called invoke that people like Marshall maybe implement that will go through all this set of rules and say, hey, it's a pointer to a member function, I should do X to invoke it, or it's a pointer to a function, I should do Y to invoke it. So there's a set of rules that let you invoke all these things. So these are the three things that are callable, which is pointers to functions, pointers to member functions, and types with call operators. There's two others that I've not listed there. The first is pointers to data members, because it's not particularly important, I think, that we talk about that case as it doesn't actually do anything. Invoking a data member, of course, doesn't execute any code. And the other one is that if you have a function reference, or just a function, just the name of a function, that will be implicitly converted to pointers to functions or pointers to member functions. So those three cases kind of cover it. All right, so this is probably the worst slide in the talk. So I had to talk a little bit about function pointers. And I'm sure there's at least one thing in this slide that I missed that maybe Marshall's going to point out. So which lines here are incorrect? Are any of them incorrect? All right, so first one is line 1. So we've got these three types here. Type def A is a type def of just a function type. So this is the function equivalent of an int, which is that it's just something you pass by value. It's not a reference. It's not a pointer. You cannot have these things as variables. That's not allowed, ever. So that case is not something we ever deal with. So then there's the other two. There's B, this type B, and this type C. So B is a reference to a function. And C is a pointer to a function. So the weird thing with pointers to functions and references to functions is this implicit conversion, where you've got this rule that, hey, if you've got a reference to a function, the compiler will, under the hood, sometimes convert it to a pointer to a function so that things just magically work. Which is why, for example, that B space B1 equals F, that works, and then you've got the second one there, it's not going to work because you're trying to go from a pointer to a reference. But the C space C1 equals F, that works because even though F is just the name of the function, it's not a pointer to the function. It's implicitly converted to a pointer. So there's a case that doesn't work. There's no implicit conversion. Now, for actually invoking these things, it's even more fun. So that B1 case, B2 case doesn't work because it doesn't compile at all. But the rest of those cases, they work. You can, in fact, use two different syntaxes for invoking pointers to functions. All sorts of fun. So there's another sort of thing related to callables, which is C++11 lambdas. Now, given the show of hands, I don't think I need to explain sort of the basics of what lambdas are, but if there's anybody that wants me to go over it, I will. Seemed like the whole room was pretty comfortable with it. All right. So I'm just going to step through this slide quickly. So this is, I think, the most important thing that got into the standard in C++11 from a functional programming standpoint. I don't actually think lambdas were the most important thing. I think this guy was. So std function is a generalized function wrapper. What that means is anything that's a callable, you can stick into one of these. given that it has the correct signature. And then you can just call it as if it was a function. It has a call operator, and it just works. So you don't have to worry about any of that weird syntax from the last slide. That was completely useless information now. Nobody except me, Marshall, a couple other people need to know that. All right, so the examples in this talk ironically catalog the different phases of me as a programmer. So back when I was like 17, which was not that long ago, and I say that because somebody would point out I shouldn't be saying back, it was fairly recently. But I used to enjoy playing and then developing text-based games. So these things would be called MUDs, multi-user dungeons. These things were like from the 90s. Very old school. And so it would just be text-based. Everybody would log in. It would use a reverse telnet over TCP. If you've never heard of reverse telnet, go Google it. It's a pretty cool way of connecting to something. And so you'd have a game world. You'd have rooms. You'd have mobs, so like AI, and items. And almost every one of these games had some sort of in-house scripting language. And it was always written differently. No two games had the same one. I'm not that familiar with the gaming industry, but I'm pretty sure it's somewhat like that. Pretty much every game has some amount of scripting language that they use for doing the development of the game world. You want to try to keep as much of the sort of game world out of the core code that's, in C++. You want to put as many things as possible into scripts. So, for example, you'd have like a room program. Like rooms would have a couple directions. So you'd have like a room would have an east direction, a west direction, a south direction, and north direction. And sometimes when a player enters a room, you'd want to have something happen. So let's say we have a room with a dragon in it, and the player enters the room from the east. And so we want to run this little program. So print out some message, wait 10 seconds, wake up the dragon, and kill the player. Well, maybe the player kills the dragon. So this is what the data structure for the room looks like. So you got some ID. It's got the name of the room, the description. It's going to be printed when the player types look room, a whole bunch of other stuff. It's going to have some methods. And then it's going to have a whole bunch of different triggers. So it used to be back in the older codes when they were all written in C, these would just be pointers to functions. These days, a couple games, some of which I worked on, would use std function or its predecessor, boost function. So the idea was that you were going to have something like this, which was going to take in some just std string that had the program, compile the little program, and then get a function for that, stick it into that trigger list, and then we'd have some way of putting it into a database so that we could load it later. One of the reasons that we liked using std function was that sometimes we'd have one or two of these little programs which would be like a bazillion lines, and if it didn't work, the game didn't work at all. So we would just say, okay, we're going to hard code that. But we still wanted to sort of use the same interface. We don't want to have, some of these are compiled scripts, some of these are things that are hard coded. We all want to use the same sort of trigger mechanism. So then you'd have this trigger. So whenever somebody enters the room, this function gets called. And you go and check the trigger list. And if there's a trigger there, you say, hey, invoke that trigger. Wake up that dragon and kill that player. All right, so now let's talk about higher order functions. So higher order functions are functions that do either one of two things, maybe both. So it's either a function that takes a callable as an argument, or it returns a callable, or something like an std function, some representation of a callable. So you've got your standard examples, std for each, std bind. I'm a math person, so I like to think of this in terms of the differential operator. The differential operator is your sort of classical higher order function. So std for each, it takes in an argument. That is a function. But it doesn't return one. std bind both takes in a function as an argument and it returns a function. So the cool thing about higher order functions is they allow us to compose new functions from existing functions. So let's say we have some function f, takes 3 arguments. Well, maybe we want to call it with some legacy code, or for some reason we want to create a new function that always calls f with a particular parameter value. So these are pretty relevant things. So that's what we use something like stdbind for. So stdbind is a forwarding call wrapper, also called a binder. So basically it takes an argument that's a function, and then it takes a whole list of args. And those arguments are one of 4 things. If it's a member function, then the first argument should be a this pointer or a reference to an object of the correct type, because the binder needs to know what object am I going to invoke this thing on. Then you've got these placeholders. So placeholders are referring to arguments that will be passed to the binder object. So they're lazy arguments. And we'll get to an example of that in the next slide. Then we've got reference wrappers. So basically, by default, when you pass an argument into stdbind, it's going to assume that you want value semantics. And if you explicitly tell it, no, take this by reference, it will do that. All right, so this is a very colorful example. So again, we got this function, takes 3 arguments. So in this first case here, we just want to bind that first argument to be the value 17. So we're going to decrease the arity of this function, and we're going to bind a parameter. So we do stdbind :f, first argument, second one, third one. So those placeholders are referring again to the arguments in this new function that are going to be invoked. So the _1 is going to be the first argument in that new g1 function. And it's just a hint to tell the binder, hey, you need to forward that argument to this place in the bound functions argument list. All right, so here's another example. Here's one where we're taking something by reference, by const reference here. So we got some string. We don't want to copy it. Maybe it's a really long string. So again, we've got some bound parameters. Here, the parameter that we're lifting away is the last one. So we're just doing 1, 2, then 3. And so then this last one is maybe the slightly more confusing one, which is where we're just changing the order of invocation. So G3 takes the same number of arguments as F. It just takes them in a different order. And the order is specified by those placeholders again. Any questions on this? Has everybody seen this before? OK. I'm seeing a couple nods there. All right, so Lambda closures. So as I mentioned, we can capture with stdbind, by reference, by const reference, by value. You can do the same thing with lambdas. So syntax is a little bit different. Again, I'm going to kind of go over this one a little bit quickly because people seem to indicate everybody's pretty comfortable with lambdas. So the reason that stdbind, by default, tries to take everything by value is because of dangling references. So that's when you've tried to capture something by reference from your enclosing scope, and then the function that the binder function is invoked outside of the closing scope. And you have the same sort of issue with C++ 11 lambdas, where if you take something, if you enclose something by reference, and then you say return from the function, that's not good. There's nothing that's going to protect you there. So in other functional languages, a closure will keep the object alive. But C++ is not really a functional programming language. And that would have required having garbage collection sort of built into the language. All right, so binding member functions. I mentioned this a little bit earlier. So anytime we've got a member function, we just are adding another argument to the list. So like we've got this myClass add. It takes one parameter, let's say. But we have to give 2 arguments to the binder, one of which is the object it's going to operate on. And then the same thing with a lambda expression, because lambda expressions in bind basically work the same way. It's not at all true, but they can achieve the same effect. And so more commonly, you see something like this, where you're not passing in references to the object, but instead you're just passing in the this pointer. So std bind will work whether you pass in a reference to an object or the pointer to the object. All right, so next example is a little bit long. We're going to talk about Boost ASIO a little bit. So Boost ASIO is a network programming library. It uses a proactor-based design. So a proactor design is a sort of asynchronous design pattern. The spark notes on this is anytime you've got some asynchronous operation that starts, the completion handler for that operation is also an asynchronous operation itself. So you go and say, hey, start this send to some other machine. Well, whatever completion handler you have there will be treated and processed as an asynchronous event, just like the asynchronous send itself. So there's a bunch of things you can use Boost ASIO for. So this is an echo server with ASIO and lambdas. And this is all you need for it. You just include Boost ASIO, and this will do what you expect. So this is just some boilerplate code. We're creating a TCP socket, setting it up on port 2000. We've got some processing loop here. So this for loop that would just go until somebody control sees the program. There's our socket, our acceptor. We've got some buffers. So this is the cool thing. So this is this function f. This is going to be our handler for the async write and for the async receive. So we've got 2 sort of nested lambdas here. There's 2 things we need to do. We need to first sort of start a write whenever we get a message in. And then after we've written back the message, the echo, we need to start reading again. So what do? Well, we've got first this async write, which is going to take a callback. And then that callback is going to invoke that function f, which is, in fact, the thing that we're in. So this will kind of just recurse forever, going back between the async read sum and the async write. And I think this is kind of a cool little way to write a little echo server. So another nifty feature of functions and lambdas in general is that we can use them to sort of annotate code that has to be compiled in a special fashion. So who here is familiar with C++ AMP? All right, so C++ AMP is a framework for computing on GPUs in C++. Basically, there's 2 language extensions that it needs. And one of those is this thing restrict amp. And you place it on your functions. So what restrict amp says is, hey, compiler, when you compile this, you have to make sure that this is something that can be compiled on the GPU. And basically, all restrict amp means is that you can only call other functions that have restrict amp, and that you can only use certain types of data structures. And so then you pass this into some sort of a parallel for each. And so one thing I think would be cool to see in the future is, can we do restrict STM and use this to support software transactional memory in C++? All right, so these are these special data structures that you'd use with C++ AMP. We've got our parallel for each, and then we've got this lambda. And so what it's saying is it's going to keep everything by value. It uses those 2 special data structures. Obviously, it can't take them by reference because it's going over to the GPU. It's not shared memory space. And then it's just going to compute some medium quality pseudo random numbers. All right, so now I'm going to talk a little bit about parallelism. So who here is familiar with std async? Okay, tough crowd. All right, so usually when I show this chart, it's much bigger because I'm usually talking about sort of this framework I work on that has all these extensions. But I cut it down and I realized it looked very small and very big on the screen. So in C++03, we just had really one way of sort of calling functions. You would call them. They would be executed synchronously. Now in C++11, we can execute them asynchronously. So we do this with this async syntax. And what does async give you? It gives you a future. So a future is basically just an object that represents a result that's not yet been calculated. So it's just a proxy for a value you're computing at some point in the future. Then we've got this async, and it should look a lot like stdbind or any of those other forwarding constructs we worked with. So it starts a computation asynchronously, and the return value is represented by the future. So there's sort of three basic operations on futures. So you've got async, you've got this .then, which is not yet part of the standard. And that just attaches a completion handler. And the cool thing is that it gives you back a future itself, so then you can attach another completion handler to it. And you can sort of chain these operations together. And then you've got this make ready future, which just takes a value and immediately gives you a future. The cool thing is that this .then operation, when you've got this make ready future, you've got an identity element. And that .then operation is associative. So that kind of gives us a mathematical framework to reason about this. It's similar to this structure in functional programming called a monad, which is usually the sort of thing that would get mentioned at a functional programming talk. I'm not going to talk too much about that. So I did not want to use our sort of typical example, which is Fibonacci. But if you want to hear a lot about parallel Fibonacci, my boss is giving a talk today, and I bet you there will be a little bit of parallel Fibonacci there. But so I'm going to talk about an even more boring example, which is an interest calculator. So we've got some function add, which is going to take the principal. It's going to compute the interest for one period. And then we've got this interest implementation. So the serial version would look a lot like this parallel version. The only difference is that in the serial version, this central for loop would actually compute stuff. Here, it doesn't compute stuff. It's just creating the execution structure. So there's no guarantee that the computation is even started by the time that that for loop exits. So all the iterations just kind of get piled up. They're all attached onto each other. So you've got that principal equals principal.then line. I like to think of that as like a plus equals. So I'm saying, hey, take my sort of last future and sort of append to that list of iterations. So in this case, if you were to run this in serial, because there's no other processors available, it would end up queuing up all the iterations. And then when you get to that last line where it calls .get, it would go and execute them all in sequence. And of course, this is a very boring one because there's no actual parallelism here. It's just a pipeline. Everything's going to happen in order. So that's, again, we've got this .then here where we've passed it in a function. And there's a couple different ways of writing it. So is Grant Mercer here? Yep. OK, so this is Grant Mercer's code. I'm glad you're here, Grant, because I decided to put this in and not tell you. But Grant Mercer wrote this. This is part of our work on the parallel STL implementation. So this is a transform reduce, which is going to take two vectors and compute their dot products. So I think this is a pretty cool thing, especially because you remember that C++ AMP concurrency parallel for each? Well, it sure does look a lot like this, where you've got these different sort of generic routines, and the one thing they have in common is that they all take some sort of function that's going to be applied. And in fact, there's actually a parallel for each that looks a lot like C++ AMPs. So that you can take your kernels, in this case the sort of boring dot product kernel, and maybe you want to use it with a GPU, maybe you want to use it just your regular cores. And because all the algorithms are these sort of higher order functions, it's fairly easy to do that. And so of course this gives you a future, and then you could do dot then on that. So the other thing you can do with futures is you can do these sort of multi-dependencies. So this is part of the concurrency extensions proposal along with dot then. This is the somewhat lesser known part of it. So when all is just sort of saying, hey, I've got a bunch of futures. I want to turn them into one sort of dependency. So the first one there is just, they're all the same type. Give me back a future vector. And then the second one, I've got, future int, future double, future float. So it gives you a tuple. And then the last one is just if you have a vector of futures, when all will give you back a future to a vector of values. So anybody who's had any familiar with Boost Spirit will notice this seems a little bit similar to Boost Spirit's attributes and attribute grammar. The idea that you sort of need to do this unwrapping of futures and vectors of futures, because if you don't, it's not composable. You have to be able to sort of have these rules where you say, hey, if I pass you in a vector of futures, you need to be able to unwrap it out to give me just one future. All right, so this is a very boring 1D heat equation. I couldn't resist putting this in here. It's also the only example I have with WinAll that will sort of fit in one slide. So this is, if you imagine we have a rod, and it's being heated, and we want to sort of simulate how the heat's traveling through that rod. So each element's got a guy to the left and a guy to the right, and it needs to know the heat that was in that guy to the left or the guy to the right. Specifically needs to know how that heat was flowing at the previous time step. So you've got those three dependencies there. The guy to the left, the place that we're currently at the current time step, and then the guy to the right. And when you have all those things, then you can go and do the next iteration. And again, this is sort of an example where you've got purely the execution structure here. So this for loop, by the time it exits, there's no guarantee that the work's started. You've just sort of built up this vector of futures, which represents the final iteration, and has all these other futures that are sort of maybe alive, maybe not, and all these continuations that are being chained behind there. OK. All right, so we went through those slides a little bit fast. I thought we were going to have a little bit more of a introductory audience. So any questions? Yep.
You had mentioned that you work mostly on networking applications. Do you have any suggestions for good patterns for preventing dangling references? You gave the server example, but
yeah.
A client example, say where the connection might close and you want to destroy your object, create a new object, things like that.
So the way that they do it in ASIO is sort of a pass the buck style. So the owner of the connection object is whichever current handler you got. You kind of, I'm just having a little bit of trouble understanding. Can you give me an example of when it would be broken?
Let's say you send a write on your connection,
Uh-huh.
and while that write is outstanding, you just go ahead and destroy whatever dangling reference you might have found in the Lambda.
So what you want to do is you want to have all your connections be represented by shared pointers. And the way that they do this in ACO is they have this shared from this thing, which is a class that you inherit from. And shared from this basically says, hey, we're gonna if you allocated this object as a smart pointer, and you've inherited from shared from this, then you can call this method and get a smart pointer back from it. And then what you do is just every time you create a connection, you always do it in a shared pointer. And then whenever you call it, you can kind of sort of pass it around. Yeah. Oh, sorry, I should remember this one. Any other questions? Yep, Mike.
What about exceptions and futures?
So futures represent a value except when they don't. And the case when they don't is when they represent an exception. So when you call future.get, one of two things will happen. Either one, you will get a value, or two, it will throw an exception. So the idea is that sort of wherever the exception happened, that's not where you throw, because that would be a very bad place to throw. There's no way to handle that exception. So what you do is you sort of transport it to the site where it's going to be used, which is wherever you call .get or when you're calling .then, and that's where you handle the exception.
Yeah, I just wanted to comment. There's a whole bunch of mechanisms underneath future, yeah, for transporting exceptions across threads, and yeah, so they come out where you expect them.
It's even more fun when you have to do it across machines.
Certainly.
The problem, though, with transporting the exceptions across threads, and especially across machines, is that you lose the actual context. So if I want to fire up my debugger and go and actually, breakpoint where the exception happens, that's very tricky because it's not been thrown where it actually happened. And if it was on another machine, then I'm completely in trouble. So what we do in HPX is we package up the stack and stack trace, and we just send all that over the wire, but that's still not good enough. Yes. Using something that was once boost exception, but has been heavily modified. But I think one of the outstanding problems with futures is that they are very, very difficult to debug. And we need a mode where we can say, hey, I want to debug this application. I want my futures to throw immediately. Maybe it could be a launch policy, something like that. Yeah.
Yeah, I'm wondering if you could talk a little bit about your experience, your opinions about best practices. Especially, it's really easy to go in and put a Lambda expression inside of a function and then have another Lambda function inside of that Lambda, as you had one example where you had nested. Can you talk about your experiences trying to debug problems there versus using like stud function and maybe the changes and dynamics of layout, maintainability, debugging, et cetera?
So I was working over the summer with this very large multi-physics code. It was a little bit scary, and I needed to write the code very quickly, and I found myself using a lot of lambdas. What I ran into was that lambdas are very nice because they kind of keep things local. It's sort of very nice in terms of composability. But once you start looking into the debugger, it's a little bit harder to, especially if you want to breakpoint them. I found that to be really difficult. My 10 cents is that if I'm using my lambdas purely for composability, if I've put and I do this too frequently, if I do an auto, diffusion kernel in my solver just because I don't want to write a new method that's the diffusion kernel, I'm not really using the lambdas. I'm just sort of too lazy to move up 20 lines in the code and actually put it there. So I really think in most cases, you only want to be using lambdas anonymously. There's a couple of cases, maybe if I'm doing an example on a slide, where I benefit from the composability. But I think very frequently, if you're naming the lambda, you might want to be rethinking about if it's got a name, why not just make it a function? Because then it's going to be easier to debug. And the dangling reference thing, generally speaking, I don't think there's a lot of cases when you absolutely need to pass in by reference. There's a couple of them. If I've got a lock somewhere in the lambda, I've certainly got to take the lock by reference. But then there's the question, why am I locking? Because I probably shouldn't be doing that. So just pass in things by value. Try not to use lambdas purely for composability. You'll have a lot less problems. I don't know, Marshall, what's your experience with sort of from the library side, is there any way to make lambdas more debuggable or breakpointable?
I'm sure, from the library side, okay, the libraries I work on, we mostly consume lambdas. We get past lambdas instead of writing them. So I don't have a lot of experience with that. I write lambdas for test cases, and they tend to be short enough that I can debug them by inspection. The debugging lambdas, that's not really so much a language thing, that's a tooling thing. And so, or it's a tooling thing as opposed to a language or a library thing. So I don't have any great answers for that, but I'd be willing to bet that you can find people here at this conference who have thought hard about that and are working on it. Find the people who are working on GCC, find the people working on Clang, find James or one of the Microsoft compiler engineers and ask them what they're doing.
I think actually on Microsoft, debugging lambdas is a little bit better. It's been my experience, as opposed to doing it on Linux. Yeah, microphone. Oh, sorry, yeah, go, sorry.
So you mentioned that you can accomplish almost everything that bind can do with a lambda.
Yeah.
So when would you ever use bind? The only I can think of is a move-only argument.
Yes, move only. Also, if I'm trying to serialize a binder, that's a little bit tricky to do with Lambda. So with std bind, or rather our implementation of std bind, because it's a library feature, we can just go and implement the boost serialization support to send the data over the wire. I think the difference really is that std bind 1, it's been around for a while, boost bind for many years, and 2, the lambda, the type is unspecified. You don't get to know anything about the type. You have no access to that information. It's very opaque. Compiler doesn't give me any way to serialize it or to look at it at all, and that's a problem for me. Yeah. Oh, sorry.
All right. I had a question on the Echo server.
Yeah.
Or your Echo server example. Is that safe to run indefinitely with the recursion in there?
Yes, it is.
Okay. I'm not sure I understand why.
The reason why it's safe is because it's not actually recursing. So we've got that std function f. We're saying that equals this lambda, another nested lambda, the second nested lambda. That would be a good idea. Let's see. OK. So all we're doing, and here's the one where it's highlighted. In this second lambda, we are referencing that std function f. But we're not really recursing. So it's just a reference to that function there. It's not going to do anything recursive, really. We're going to have that copy. That function is going to stay alive. But there's only one instance of that.
There are obviously problems trying to capture a unique pointer in a Lambda for obvious reasons. I believe that problem is going to be solved by generalized Lambda captures.
Yes.
Could you talk more about that?
I am not qualified to talk about that because I am not up to date on that. And I don't want to give people wrong information. And I'd be afraid of doing that. Scott looks like he may be.
Basically, what it lets you do is declare a variable in the closure,
Mm-hmm.
give it an arbitrary initializing expression.
Mm-hmm.
So if you want to, for example, move a move-only type in, you would just say name of the variable to go in the closure equals standard move of whatever you want to move.
OK. So what Scott said was that it allows you to, in the closure, initialize the variable.
It actually goes in the capture.
In the capture. In the capture, you can initialize the variable from the outside scope, so that you can, take an arbitrary expression, and that allows you to move things in. And that is another major reason for the std bind. Yeah.
Maybe you already said this, but would this example work if instead of std function, we would have auto there?
I would have what?
Instead of the function f is declared as an std function object, if we had auto there, would it work?
That is a good question. I'm not sure. I don't feel like it would, because, Yeah.
Because it's auto, you can research it.
Right.
But it was a trick, and you can use the fixed point combinator so if you have a name,
Okay, so the answer Louis said is you can't do it because you can't recurse in a lambda, but there's a trick that you can do with a fixed point combinator? Okay. So I think you also might run into lifetime issues. I know I had to do this with std function for a long time. It didn't work with boost function. And I've had some issues before with lifetime problems here. So this is a little bit delicate.
Okay, thank you.
All right, any other questions? Okay.